Continuity. In order for a function to be continuous, it must meet three of these conditions. Condition number one, f of c must exist. Number two, limit as x approach to c at that point of f of x exists. And number three, first condition and second condition has to be equal to each other. So let's look at the first example. So example one. So we have a piecewise function, f of x equal to x plus 1 when x is less than 2, or f of x equal to 2x minus 1 when x is greater than or equal to 2. Is this function continuous at x equal to 2? So let's go through our three conditions. Condition number one, so at x equal to 2. So let's evaluate when f of 2. So when we evaluate f of 2, then, well, let's see. Since 2 is belong to here, right? It's x is greater than or equal to 2. So we must use the bottom function here. So 2 times 2 minus 1 equal to 3. Now let's find the limit. So f of 2 does exist. Now let's find the limit. The limit as x approaches to 2 of f of x. Well, when we try to find limit, we need to make sure we find the limit from below and from above. And if they both match the same number, then the limit exists at that number. In this case, it does. Because when we look at x from below 2, there'll be this function right here. If we plug in 2, you get 3. If you plug into the second one, okay, when it's approached from above, also equal to 3. Since 3 equal to 3, so limit as x approaches to 2 of f of x equal to 3. And since our first condition, 3, second condition also equals to 3, they equal to each other. So we say f of x is continuous at x equal to 2. If you look at our function, before 2 is going to follow this line right here, x plus 1. And after 2, you're going to start at that point, then go up and then follow the second part of the function, 2x minus 1. And it's continuous in one smooth notion. There's no breakage or anything like that. Okay. Now let's look at other example. For example, like example number 2. So you have the same equation, except there's equal signs missing here. Well, if equal signs missing, that means f of 2 doesn't exist. You already failed the first condition. So if you look at the graph, this is what the graph looked like. So the same as before, you follow the bottom line here. The bottom line is 2x plus 1. But at this point, there's a hole there because f of 2 does not exist. Then you follow by the second line, 2x minus 1. So what happened is this particular function, if it's written this way, is now not continuous. Okay, because it discontinued at what, x equal to 2. X equal to 2, you have to skip and then lift up your pencil and continue. Okay, if you have this type of situation, we call it removable discontinuity. Now for the example 3 right here. So we have the same equation again, but let's see what's the difference here. So first of all, we try to verify if f of 2 exists. It does. Okay, so we punch in, since we want f of 2, we have to follow the bottom equation. So 2 times 2 plus 1, so equal to 5. It does exist. But the limit, however, do not exist. Because when you plug in 2 to the top function, you end up with 3. But if you plug in 2 on the bottom, so we try to figure out a limit as x approaches 2 from below and above. Below, you get a 3. Above, you get a 5. They don't match. Therefore, the second condition of the limit of the continuity doesn't exist. So in that case, then you have a discontinuity. But what type of discontinuity is this? This is called a jump discontinuity because while you follow this line right here, at that point, you jump up, but instead of continue from here, you actually jump up to for an f of 2 is equal to 5. So you definitely show a discontinuity here. Your function start right here on the bottom line, it jump and then go up to continue from the top line. Now let's look at this type of continuity. So we have another continuity now, but this time you have 3 equations, 3 piecewise functions. The first one is x plus 1. So from below you have this line right here, and then x at x equal to 2, you're actually at this point. But after that, you continue from that line. So, all right. So in this case, let's see what happens. The function does exist at 2, and limit does exist. But the difference is these two numbers doesn't match. So your condition 3 failed. So when you have your condition 3 failed, that means your function does exist. At that point, your limit also exists. But the function, but condition 1 doesn't equal to condition 2. Therefore, you have what we call a point discontinuity. Okay. Now, whenever you have a rational expression, you're definitely going to have this type of graph. Like we see this back in previous chapters when you have the x squared, 1 over x squared, or 1 over x, right? Things like that. Okay. When you have a rational expression, you're always going to have some kind of vertical asymptote because whatever make the denominator equal to 0, that's where you're going to have asymptote. In this case, any graph that has asymptotes, it obviously is not going to be continuous, and we call that essential discontinuity. Now, the last example is kind of going backwards. We're saying for what value of a, so we'll try to solve a here, is the function, okay, so you have a piecewise function like before that continues at x equal to 4. So if you want this function to be continuous at x equal to 4, then what would this a need to be in order for that to happen? Now, so all you have to do is think the three conditions. So as soon as we let the first condition, we want to make sure f of 4 exists. And we want to let the second condition, the limit also exists at that point, right? So what we did is we plug in, right? We plug in 4 into the into this bottom one here. Okay. So f of 4, I mean, this must equal to the same thing, right? Okay. So if you take, you basically just want to set the first condition equal to the second condition, and if that's the case, leave the a out, then you can solve for a easily. So once again, f of 4, because we have to follow this one, right? Okay, because the first condition. So when you plug in 4, 4 squared minus 4, that give you 12. So we know f of 4 equal to 12. Then the second condition says the limit at this point, okay, has also equal to 12. So if you, the limit, that means it doesn't matter which one you use, they have to be the same number, and it has to be 12, right? So we know this function up here, whatever this is, has to equal to 12. So 4a plus 5 must equal to 12, because we're going to plug in 4 in for x, so when you solve for a, you get 7 over 4.